So let's talk about looking at the short-run behavior of our rational functions. Now, some of these pieces we've talked about before, and then we have kind of one little new piece. So the vertical asymptote, and there can be more than one of these, so you might have multiple vertical asymptotes, and that occurs that when we look at the denominator, that's where our denominator is equal to 0. Now, something I'm going to be throwing in here is the simplified form. So with our rational functions, when we're looking at short-run behavior, one of the first things we're going to do is factor, if it's not already factored. And then something we're going to do then is simplify. So we might have some of these factors cancel out with each other. So it's in the simplified form that then we'll look at setting the denominator equal to 0. And those spots is where our function would be undefined. So it would be these kind of restrictions on our domain, and that sets up our vertical asymptote. It's giving us these values that our function cannot equal. So it kind of creates these vertical barriers. We're also going to look at the zeros of the function. So this too, we're going to be looking at the simplified form of our rational function. And with that, we're looking at where the numerator is equal to 0. So with that, we can just grab the numerator, look at the zeros, and that gives us some coordinates for our graph. If we have zeros, there might be cases where we don't cross the x-axis at all. Now, a new piece is looking at holes on the graph. So there can be these little holes on our function where our function's undefined. It isn't making a vertical asymptote though. So this is going to become apparent in these first two steps that we do. When we factor and then simplify, these factors that we cancel out, those are the spots where holes are occurring. So with this one, we're kind of not really looking at the simplified form nor the original form. We're looking at this step in between where we cancel out values. So this factor that cancels, that will give us some value c where our domain's restricted. We can't be equal to that value, and it'll create a hole in our graph. So let's look at some examples here. So we're going to look at the zeros, holes, vertical asymptotes, and then we're also going to throw in some practice with our horizontal asymptotes in here as well. So first thing we want to do is factor. So we'll need to refresh those factoring skills. So with these, we can just factor directly, and same thing for the denominator. And if these get tricky to factor, you can always take them into side work and just do the work of factoring the numerator, and then do the work of factoring the denominator, and then you could put it all together in your rational function. That's a great way to organize your work as well. So with this one, I need two values that multiply to -6 and add up to -5. So with that, I'll have a +1 and a -6. And then for the denominator, two values that multiply to -12 but add up to +1. So that'll be a -3 and a +4. So there's my factored form. And now what I would do is look for any pieces that would cancel out, which we don't have here. So that's all done. So let's go through our pieces, and you can do this in any order that you want to. Something I could make note of right now is that since nothing canceled, there are going to be no holes in the graph. So that part's done. What we could do is go to zeros of the graph. So with the zeros, think of this as taking your numerator and setting it equal to 0. So we're going to take 0 equals in the numerator of this factored form. So that x + 1, x - 6. And if we did have pieces that canceled out here, we would use this most simplified form for plugging in here for the numerator. But since nothing canceled out, we have this whole x + 1, x - 6. And then we just solve. So x + 1 has to equal 0, or x - 6 has to equal 0. So we get x equals -1, x equals +6. So this gives us two coordinates. We have -1, 0 and +6, 0. So we have two coordinates that we could graph here. We could go on to our vertical asymptote now. Now, with the vertical asymptote, this is where we're taking our denominator and setting it equal to 0. So we're looking for where our function would be undefined. So solving 0 equals, and then the factored form of the denominator, x minus 3 times x plus 4. So we'll have x minus 3 equals 0, so x equals 3. X plus 4 equals 0, x equals negative 4. Now with this case, this is giving us lines, so it's not coordinates. So we have this line at x equals 3 and x equals negative 4 that are creating these vertical asymptotes. And our last piece that we'll put in here is the horizontal asymptote. So with this, we'll just use what we did in the previous video. So with this one, if you have the unfactored form, that's easiest. So we want to compare the degrees of the numerator and denominator. And what we can see is we have degree 2 and degree 2. So this is the case where m is equal to n. So with that, when we find our equation for our horizontal asymptote, we're going to use the division of our leading coefficients. So with this case, it's like we have a leading coefficient of 1 and leading coefficient of 1. So it's those values. In fact, I'll even draw those in. It's like we have 1 times and 1 times. So finding our horizontal asymptote, we divide those two values. So 1 divided by 1, which is just 1. So this is also creating a line. That's our horizontal asymptote at y equals 1. So with this, let me just show you how we could start kind of building a graph or a sketch just based on this information. I'm not even going to set a scale, just to kind of show you how it would come together. So the zeros of the graph would be coordinates. So we'd have a coordinate like negative 1 and positive 6. Again, I'm just kind of estimating here so we can see how it comes together. We have a vertical asymptote at x equals 3. So we're going to have this vertical line that we can't cross at about 3. And at negative 4, we'll have a vertical line that we can't cross. And then for our horizontal asymptote, for the long run behavior, we're going to see our graph approach y equals positive 1. And beyond that, I really can't graph anything else just based on this information. So this is a bit different than what we saw with the polynomials and previous graphs where you could really see a lot of information. With these, it's just trickier, but this does give us a good structure to follow in terms of short run and long run behavior. So let's look at the graph and see how we can kind of fill in the blanks here. So our graph is doing something like this. So we can see is our zeros, negative 1 and positive 6 there. We could even, if you needed to find the, I've lost the word for it, y-intercept, that's just plugging in x equals 0 into the function. So you can always find that as well if you need another coordinate to graph. But even with that, it would be hard to see what everything is going on. So at x equals negative 4, we can see this kind of vertical barrier that our graph is not crossing. Same thing at positive 3 here. Oops, right there, positive 3. And then at y equals 1, we can see that's working for our horizontal asymptote in terms of what our graph is approaching. So just to get a sketch here, what we're seeing for our function is something like this. Then here we're crossing, going off to our vertical intercept there. And then for this side of the graph, it did something like this. So putting it together, we have the zeros as coordinates, vertical asymptotes as these barriers that we cannot cross, and then this horizontal asymptote that we can cross in the short run behavior, but then in long run behavior, we should be seeing our function approach that horizontal line. All right, With this one, I need to factor. So I'm going to have 3 over, and then the denominator, there's a common factor of x. So I'll leave us with x squared minus 4. But that's not quite done yet. We have the difference of squares. So this is going to be 3 over x times x minus 2 times x plus 2. And then I look and see if anything can cancel, which it cannot. So with that, this will also have no holes. For the zeros, so we take our numerator and set it equal to 0, which in this case gives a false statement. So that's not true. So what that tells me is that there are no zeros for this graph. So we are not going to cross the x-axis, which is completely fine. That works. Vertical asymptote is where we take the denominator and set it equal to 0. So 0 equals x times x minus 2 times x plus 2. So what we'll get from this is we'll have 3 vertical asymptotes. So we're going to have x equals 0. From the x minus 2 equals 0, we're going to get x equals positive 2. From x plus 2 equals 0, we'll get x equals negative 2. So we're going to have these 3 vertical lines coming through. Now for the horizontal asymptote, we need to compare the degree of the numerator and the denominator. So I'm going to go back to this unsimplified form here. So in the numerator, this would have a degree of 0, because it's like there's x to the 0 power there technically, which just turns into multiplying with 1. So we have m equals 0 and n equals 3. So this is a case where m is smaller than n. And with that, we get a horizontal asymptote of just y equals 0. So for our graph, in terms of the information I have here, we're going to have 3 vertical asymptotes. So one actually along the y-axis, and then positive 2 and negative 2. And then for a horizontal asymptote, it'll be the x-axis. So to take a look at this graph, we can see we are not crossing the x-axis, so there are no zeros showing up. In the long run, we approach y equals 0, which is fantastic. And then we have, I paused there because the vertical asymptotes don't match up, but it's a typo. Put a 2 there, it should be a 3. There we go. Okay, so we still don't cross the x-axis, so no zeros. And we approach 0 in the long run, so our horizontal asymptote works. And then for our vertical asymptotes, we have negative 2, 0, positive 2. So you get a really interesting graph coming through here. So to just get a sketch of that down here, we have something like that. And then we have these kind of parabolas and parabola, and then something up here. All right, 2 more of these. And this is going to end up being kind of a big video, but lots of good pieces to practice here. So in the numerator, I'm going to factor out a common factor of 3. So I'll give us x minus 2 over, and then the denominator, I can just factor this with x. So 2 values that multiply to negative 6 and add up to positive 1. So it's going to come from a negative 2 and a positive 3. Now what I have here is a common factor that I can divide out. So those x minus 2 values will cancel. I want to keep that in mind though, because that's important for finding the hole in the graph. So this is going to simplify to 3 over x plus 3. So that's my simplified form that we're going to work with here. So let's go ahead and start with the hole in the graph, since that's a new one for us. So it's coming from that x minus 2 that we just canceled out, which means we're going to be working with the value x equals positive 2. So there's going to be that transition that we see with our vertical asymptote and with those zeros, that seeing it in the factored form, the sign flips. So we're looking at x equals 2. And what I'm going to do is look at r of 2. So I want to plug in 2 into the function. Now, if I plug it into this original form, which you can try out in your calculator, it's going to come out undefined. Because if I plug in 2 and plug in 2, we're going to end up with a 0 in the denominator. So when you plug in, use the simplified form. So we're going to use 3 over 2 plus 3, which will give us 3/5. So what we're going to do is write this coordinate down, this coordinate 2 3/5. And when we look at the graph in Desmos, I'll show you what's happening there. But we're going to have this hole in the graph. All right, zeros is where we take our numerator and set it equal to 0. But again, this is just creating a false statement since we don't have our variable in there. So that does not work. So that just tells us that there are no zeros on our graph. Vertical asymptote is where we have our denominator equal to 0 and we're using our simplified form here. So for the rest of the pieces, we're going to use our simplified form as we go through. All we need from this unsimplified form is what we canceled out so that we know our x value for the hole in the graph. Subtracting 3 from both sides, that'll be at x equals -3. So we're going to have this vertical line at -3 that we cannot cross. For the horizontal asymptote, really for this you can use either form. Should all work out in the end. So I'm going to go back a little bit on what I said earlier of saying we're only using the simplified form, and here we're going to look at the unsimplified form. So with this, our degree for the numerator is 1, and the degree for the denominator is 2. So comparing these, the degree of the numerator is less than the degree of the denominator. So with this, we want to look at, we just want y equals 0. These rules for the horizontal asymptote, you can hear me probably pause a bit because I need to think before I do it each time. They're hard to memorize, so just write down those rules on a little piece of paper to have it as easy reference. In fact, all of these little rules that we have, because it just takes practice with them in order to get them down. So y equals 0. So for this graph that we're seeing here, we're going to have, so no zeros. If I think about this 2 3/5 that we're going to be graphing, so that's going to come through as a hole in the graph. So I'm just going to make a little mark there to represent 2 3/5. And then we're going to have a vertical asymptote at -3, so like out there-ish. And then horizontal asymptote is going to be along the x-axis. So looking at the graph here, what we can see is vertical asymptote out here at -3. Our long run behavior is going towards 0. And let's look at what's happening at 2 3/5. Because in this graph, it doesn't look like anything's happening. And even with Desmos, if you zoom in and in and in and in, it looks continuous. It doesn't look like anything's happening there. But what we can do, so with Desmos, you can click on the line and then kind of drag around to see different points coming through. And if I can get it right, it can be tricky. Ooh, you can probably see it flashing. Sorry, it's really, there we go. 2 undefined. So where it's graphing 3/5 there at 0.6, it's not actually plotting a point. So at that very specific spot on our graph, we actually have an empty hole. So how I would draw a sketch of this is we're seeing something down here. And then above, it's like we have something and it's going to graph there, but then we skip over it and then it continues on. So where it looks like you would just draw right through it when looking at Desmos, we have to know that there's actually a little hole there where our function's undefined. And this affects the domain of our function too. If I was writing the domain, I would have to be thinking about, okay, x cannot equal -3. Also, x cannot equal +2. All right, one more example here with the factored form. So it's already factored, and then if I simplify, all that I would need to do is take out the x minus 1 values. So without those, I would have my factored form. In fact, I'll write it out. 2 times x plus 7 squared over x plus 3 times x plus 4. All right, let's take care of the whole first, just while that's fresh in our memory. So we crossed out x minus 1. So that tells me that x equals +1. So I need to look at r of +1 using the simplified form. So 2 times 1 plus 7 squared over 1 plus 3 times 1 plus 4. If we just grab a decimal for that, that should be at 6.4. So we're going to have this coordinate, well, rather this lack of a coordinate at 1, 6.4. So we'll have a little hole in our graph right there. For the zeros of the graph, we're going to set the numerator equal to 0. So with this, we'll just have that x plus 7 equals 0. So x equals -7. And I'm just going to make a little note about the multiplicity there. This has a multiplicity of 2 with that square coming up. And remember, with our graphs, this is true of our rational function along with our polynomial. That means at that point, we're going to see a bounce. So it's kind of going to look like a parabola zoomed in at that point there. Vertical asymptote is where we set the denominator equal to 0, and we're using our simplified form here. So x plus 3 and x plus 4 equals 0. So we're going to have a vertical asymptote at x equals -3 and x equals -4. And then our last piece here is the horizontal asymptote. Which, if we go back to our original forms here, so if I just think about the leading term of the numerator and the denominator. So in the numerator, if I think about, I want to keep that x minus 1 in there. So I would have 2 times x squared. So like we did with the polynomials, we could FOIL it all out. But really, this leading term is going to come from just multiplying those x values together. We also need that number that would be multiplying on as well. So in the numerator, we'd have this leading term of 2x cubed, sorry. We have x times x squared. And in the denominator, we would have x times x times x. So there's no extra number multiplying outside. So that would just be x cubed. So this is a case where the degree of the numerator and degree of the denominator are the same, since they're both degree 3. So what we would do is take the division of the numerical coefficients. So at 2, and then it's like there's a 1. This would be 2 over 1, which is just 2. So in terms of building a sketch of this, we have a hole in the graph at 1, 6.4. So I'm just going to kind of draw a little hole there. Zeros, we'll have one at -7, so somewhere out here. And then I know it's going to bounce there, so either it depends on what side of the graph I'm on, but we're either going to have kind of a parabola above or below. Vertical asymptote at -3 and -4, so they're right next to each other. I know my scale's a bit off there, but that's fine. It's just a sketch. And then y equals +2, we'll have this vertical asymptote. So let's look at the graph here. All right. So what we're seeing is Okay, y equals positive 2. We're approaching that in the long run on both sides of the equation. For the hole in the graph, somewhere in here, if I could get to exactly 1, we're going to see that word undefined pop up as I kind of move between those points. There it is. 0 at -1, and we can, or at -7, and we can see the bounce off of that point like we expected. And I think with that, oh, and then at -3 and -4, we have 2 vertical asymptotes. So it's making kind of this big gap here between those 2 values. So we're going to have this little area where we're not graphing anything. So just to draw this sketch, so this is coming from our vertical asymptote, and then we bounce, and then it approaches in the long run, something like that. And then here, same idea, it kind of approaches from our vertical asymptote and then goes towards our horizontal asymptote in the long run. Okay, I know that was a big one, but there were a lot of scenarios and pieces to cover. So factor, simplify, and that can help you find the hole, and then the zeros of the graph, vertical asymptote, and then horizontal asymptote.